Hello and welcome to another episode of Season 5 Crops TV. I'm Dr. Richard Roth, Assistant Professor and Extension Nitrogen Science Specialist in the Department of Agronomy at Iowa State University. And today I'm going to talk about nitrification inhibitors and what the science says about them. So the first thing that I want to share with you today is a QR code that you can use to reach the website for my lab. The reason that I'm showing this is while you will have this video record of this presentation, I also want to give you access to a physical copy of it. And so you can visit this website, click on the research tab, and click on the inhibitor project, and you will find a link to the actual presentation that you see today. So as we move through today, we're going to basically focus on three main areas. Number one is we'll do a quick rehash of the nitrogen cycle and some of the processes that go on within it. Number two is we will talk about what nitrification inhibitors are and also how they work. And then number three is we will look at some of the previous science that has been done on how well these products work. So we'll start with the nitrogen cycle. What I'm showing here is a simplified version of what the nitrogen cycle looks like. So if you've ever taken a soil fertility class or listened to a soil fertility specialist talk, you've probably seen something similar to this. I say it's simplified because a lot of these processes on here are multi-step. They're facilitated by microbes and things of that nature. But really, I think the thing for you to take away here is that it's not a simple add fertilizer to the soil and it's available, right? There's a lot of different transformations that can happen, losses, additions, things of that nature. So the first process that I want to talk about today is called mineralization. To put this really simply, this is when we transition from organic nitrogen to plant available nitrogen. So you'll see there at the top, the simple version of it is I've indicated as soil organic matter being mineralized by microbes, with the end product being ammonium, which is a plant available form of nitrogen. It's the NH4 plus version of plant available nitrogen, so the positively charged inorganic nitrogen ion. Now this process, it is multiple steps, as you can see there, kind of highlighted on the bottom. The first is that you go from that organic matter into basically an amino acid, and then that amino acid is then converted into ammonium. But what I want to kind of highlight here is for anybody who may use urea as a nitrogen source. Okay, so an easy way to think of how urea reacts in the soil is that it actually would kind of start in that middle portion of this process. Now it's a slightly different reaction that occurs, but essentially when we add urea, it's in the form that we find in the middle of this process, and so urea is pretty quickly converted over to ammonium. The other thing that I want to highlight about this process is that it is reversible, and so the reverse of mineralization is known as immobilization. So that is when plant available nitrogen is removed from the soil solution and made unavailable. And so this typically happens when the microbes in the soil are trying to break down high carbon residues. So think things like corn stalks, cereal rye residues, maybe even some manures, things of that nature, right? They're trying to break down that carbon source. And in order to do that, they need to utilize nitrogen from somewhere. And the place that they take that nitrogen from is the plant available pool of nitrogen. So essentially, we're taking the ammonium or the nitrate and we're incorporating that into the microbial community, and so that it's no longer available for plants to use. Okay, so the next process in the nitrogen cycle that I really want to touch on today is nitrification. And so this will be the most important for us today because we're going to look at nitrification inhibitors. And so what we need to know about nitrification is that it's the conversion of ammonium, so that's your NH4 plus, into nitrate. That's your NO3 minus. We've probably all heard of nitrate. as being detrimental to water quality and things of that nature, right? We're very familiar with nitrate. So this is how we get from ammonium to nitrate. So the first thing that I want to highlight here is that the ammonium that goes through this process, it doesn't matter where it comes from. It could come from fertilizer that you add to the soil. It could come from manures. It could come from different residues decomposing. It could come through atmospheric fixation, right? It doesn't matter. Ammonium is ammonium, and it's going to go through this nitrification process. So, this process is actually two steps. So, the first step is the conversion of ammonium to a molecule that we call nitrite. So this is NO2 minus. So you may or may not have heard of nitrite before. If you haven't, that's fine. It doesn't exist in our soils for very long. And in fact, we don't want it to exist in our soils in a large amount because it can actually be toxic to plants. If you've ever taken a soil fertility course or heard a soil fertility specialist talk, you've probably heard somebody at some point mention that nitrification is facilitated by microbes, and the one that you've probably heard is nitrosomonas. Now, nitrosomonas is one of the microbes responsible for this first step in the nitrification process, but actually there's dozens and dozens of different microbes and also non-bacteria microbes as well that help facilitate this step in the process. Now, the second step is when we convert from that nitrite molecule into nitrate, again, that NO3 minus that we've all heard of. And again, this is a microbially facilitated process. And for those who are familiar, you've probably heard of Nitrobacter. It's the microbe that tends to get all the shine when it comes to the nitrification process. But again, just like the first step, there's dozens of different microbes that can help facilitate this second step in the process as well. So, a couple things that I want to highlight about nitrification is that it's very much tied to microbial activity. So, hopefully, we've all heard the recommendation that we should not apply any nitrogen in the fall until soil temperatures drop below 50 degrees. And I'm sure that there's tried to be some kind of explanation about why this is the case, but I'm going to try to reiterate why we try to apply below 50 degrees in the soil. So, the primary reason is that once we drop below 50 degrees, the microbial activity in the soil tends to slow down. And the further that we get below 50 degrees Fahrenheit, the less active the microbes actually are. And so, if we reduce the microbial activity in the soil, we reduce the amount of nitrification that's occurring, meaning that we keep more ammonium in the soil rather than converting to nitrate, which has the potential to be lost. So, some other things that can kind of control this nitrification process are soil aeration and soil moisture. So, that's kind of a double edged sword, right? So, typically, the more water that you have in the soil, the less air. And then the less water, the more air. And it's really important that we understand this concept because the bacteria that are responsible for this nitrification process are what we call aerobic, meaning that they need oxygen in order to metabolize this nitrogen. So if you're in a highly saturated soil system, you'll tend to see this nitrification process slow down. And in fact, you'll see a different process that we'll talk about in a minute called denitrification increase and speed up. And then the final thing that I want to really mention about this nitrification process and why we recommend applying below 50 degrees soil temperature is that if you were to apply nitrogen into an ideal soil temperature, let's say 65, 70, or higher degrees Fahrenheit, what can happen is that all of the ammonium that you put into the soil can be gone or nitrified into nitrate within just 2 to 3 weeks. The warmer it is, the less stable the ammonium is in the soil, meaning that it converts to nitrate. And the faster it does that, the faster that nitrogen is susceptible to being lost through these different loss pathways. So, as I mentioned, there is loss pathways. And so that nitrate could be lost through leaching, which pretty sure most people are familiar with, and then denitrification. So, for those unfamiliar with leaching, it is simply the movement of nitrate with water below the root zone. And so, in our heavily tile drained landscapes, especially here in Iowa or other states in the Midwest, the tile drainage basically provides an unobstructed pathway for the water to leave the field. The more nitrate that's in the soil, the more potential there is for that to move with water down to these tile systems and then out of our fields into the waterways. And so this is what is causing the majority of the nitrogen related water quality issues that you may hear of from the Midwest. The other loss pathway that I mentioned is denitrification. Most people are maybe familiar with the fact that we can lose nitrogen as a gas from our soils, but maybe you're not familiar with the actual name of the process. And so denitrification is essentially when you're in a saturated soil system, the microbes, there's a lack of oxygen in the system. And so the microbes need oxygen in order to live. Since there's no oxygen in the soil, they need to get that oxygen from somewhere. And so these microbes that are responsible for this denitrification process actually utilize the oxygen from those nitrate molecules and then emit, or the waste product from this process is these nitrogen gases that they emit from the soil. So, like I said, this is really high risk in poorly drained soils. If you have ponding in your fields, that's the areas where you're going to see denitrification be the highest. I think that's something to remember is that denitrification may not be even across your fields, but if you have areas that you know are prone to ponding and standing water, those are areas where the highest risk for losing this nitrogen occurs. This process speeds up just like nitrification slows down below 50 degrees. Denitrification tends to speed up the higher you get above 50 degrees. And while it does take a couple days of saturation for this process to ramp up, once it's really going, you can lose nitrogen pretty fast. So you can see there on the table at the bottom, the warmer the temperature you get, the greater percentage of loss per day you can have. For example, if you are saturated for a 12-day period, it'll take 2 days to ramp up, and then you have 10 days of loss that could be occurring. That could be anywhere from 20 to 50% loss of all of the nitrogen in your soil. So we can lose a lot of nitrogen through this process. And so the next thing that we're going to do is we're going to talk about nitrification inhibitors. And the first thing that we'll ask is, what are they? So it's actually a pretty simple answer. So nitrification inhibitors are simply chemicals that disrupt the nitrification process. So they disrupt that conversion of ammonium into nitrate. But more specifically, they tend to target the first step of this nitrification process. And there's a reason why they tend to target this step. And that's because, as I mentioned earlier, we don't want nitrite to build up in our soils. It can be toxic to the plants. And so we target this first step in the process because that way, if any of that ammonium does squeak through and make it into nitrite, then those nitrobacter and those other bacteria and microbes responsible for the second step can then finish the conversion all the way out to nitrate, so we don't have a buildup of nitrite in our soils. And when we think about nitrification inhibitors, there's two general types, there's two general classifications. The first is biological nitrification inhibitors, and then the second is the ones that we are generally more familiar with, and that's the synthetic nitrification inhibitors. So in this presentation, I'm going to focus on the synthetic inhibitors, but I will just give a brief overview of biological inhibitors in just a second. So let's rehash why we want to keep the nitrogen as ammonium in our soils. The soil has a charge to it, right? We've all heard of cation exchange capacity or the exchange sites in the soil, and that is related to the charge of the soil. So soil has a negative charge. And so the reason why we want to keep the nitrogen as ammonium is because those ammonium molecules have a positive charge. So think about if you have two magnets. When you try to attach two magnets, you're sticking the positive end of one magnet to the negative end of the other. And while that's a gross oversimplification, that's essentially what's occurring in our soils is that positive charge on the ammonium can bind with the negative charge on the soils and be held more tightly. So if we were to allow that ammonium to convert out to nitrate, that NO3 minus, right? So it has a negative charge on it. That'd be like trying to stick two negative ends of two magnets together. It just doesn't work. That's why we want to keep it in the ammonium form. So biological nitrification inhibitors. As I mentioned, I'm not going to spend a lot of time here. And there's a couple of reasons for that. Number one is because there's just not a lot of information available on these. And the second is that there's just not a lot to be said here. So the easy way to describe what these are is that they are chemicals that are exuded by different plant roots, which exhibit some level of nitrification inhibition. So the most common plant that has been studied is sorghum, though almost all plants do exude some level of these chemicals. Okay, so corn, soybeans, wheat, rice, other small grains. The problem right now with kind of being reliant on these is that we don't know which of these and from what plants remain in the root zone, which of them move out of the root zone with water. We don't know how effective they are. And so there are groups around the country working on this. I'm not specifically working on this in my group, but I think it's important to understand that these exist, but whether or not they can be an effective tool, especially in our systems here in the Midwest, remains to be seen. The real issue with using these within our systems is that these plants that are going to exude these chemicals have to be growing at the time of application. And quite often, we don't generally have plants growing in our systems at the time of nitrogen applications, unless, of course, you are using a cover crop or you are applying nitrogen in season as side dress. And so, but even then, we're still unsure at the level of efficacy that these chemicals from, let's say, a cereal rye root or a corn root may actually have. The products that we are familiar with are going to be our synthetic nitrification inhibitors. And in general, you can kind of classify these into three really common active ingredients. The first is going to be nitropyrin. So these are products like Inserve or Instinct. But what I'll say is that nitropyrin is no longer patent protected. And so it's possible that you can also see nitropyrin be listed in products that are not Inserve or Instinct, which are the most common. The second active ingredient that you'll quite often see is going to be DCD, which stands for dicyandiamide. And so, like nitropyrin, this product is also not patent protected. And so, you'll see this in a lot of different formulations. Most co-ops nowadays have some formulation of DCD that they will have available for use. Typically, these products are the DCD molecule plus something else, and whether or not that something else provides a benefit to you depends on your specific situation. So, for instance, here, the products that you see listed. So, Source DCD, that would be a product that only has this DCD molecule in it as the active ingredient. But then you move down to where we have function, and that would be the DCD molecule plus some sulfur. They don't really say how much sulfur, but if you're looking to add sulfur to your system and you want to use a DCD product, maybe this is a good choice. And then finally, there's this Trident N product. This product is actually DCD plus a urease inhibitor known as NBPT. So there's also other products out there. If you've ever heard of Agritane Plus, also has these same kind of active ingredients, right? So in this case, you may be protecting against both urea hydrolysis, so transitioning from urea into ammonium, and then also the ammonium into nitrate. So if you're using urea, you might consider a product like this. If you're using a liquid fertilizer such as UAN, you may also consider this, especially if you are going to broadcast that fertilizer and not incorporate into the soil. And then finally, the newest product available, and it's been out for a couple years now, is pronitridine. And so that is going to be uh, the product that you'll see with that is Centuro. So pronitridine is a patent protected product still, so you will only see that in the Centuro products. There's other active ingredients that exist, and I'll mention a couple here in a second, but these are the most common that are on the market right now. And amongst these active ingredients, there is essentially two modes of action in terms of how they inhibit nitrification. So, the way that we would typically think about nitrification occurring is the ammonium would bind to a receptor site on a microbe. So, the pink area there is my representation of a microbe in the soil. So, let's say Nitrosomonas. And where you see AMO listed there, that stands for ammonium monooxygenase. All you need to know is that that is the chemical inside the microbe that is responsible for the conversion of ammonium into nitrite. So, that first step in the nitrification process. So, typically, what would happen is the ammonium would bind to the microbe, that AMO enzyme would activate, and out comes nitrite. Now, these different products, like I said, there's two modes of action. So the first is where the actual molecule of the active ingredient in the inhibitor is shaped in such a way that it can actually mimic ammonium. And so in that case, the inhibitor can actually go in and bind to the receptor site there on the microbe. And so what that actually causes is then the ammonium can no longer bind to that receptor site, and so it's not being converted into nitrite. So that's the first mode of action. The second mode of action is where the inhibitor product actually, for lack of a better term, it infects the microbe, right? So it makes its way inside the microbe and it disrupts that AMO chemical that's inside of the microbe. So it makes it so that the microbe cannot activate that AMO enzyme. So in this case, the ammonium may still bind to the receptor site there on the microbe, but it's not going to be converted to nitrite because of that AMO enzyme being unable to activate. So, as I mentioned, there's also some less common products. And so those include things like calcium polysaccharide products. So, a commercial product that you may hear of with this active ingredient would be Enzone. And then there's also some thought that humic acid products may help prevent some nitrification. So, the way that these work is that they're supposed to provide essentially high CEC molecules within the soil. And so these offer alternate exchange sites for the ammonium to bind to so that it is binding to those exchange sites rather than the receptor sites in the microbes. Research on these products in terms of nitrification is still lacking. And so I can't say one way or the other how effective these products may be, but you may see them on the market. And so just know that they are available and that they could have some nitrification inhibitor properties. So we've talked about the nitrogen cycle, we've talked about what these nitrification inhibitors are. Now let's talk about what the science says about how well they work. So as we jump in to this section of the presentation, I will preface with a lot of this research that I'm going to show you is older. Okay, so at least in most cases, at least 10 years old, right? So in that time frame, formulations of these products could have changed, but that's what's available for me to show you. The other thing that I want to highlight is that a majority of what you'll see is related to anhydrous ammonia applications. Though, as I stated up front, right, it doesn't matter if the ammonium in the soil is coming from anhydrous or it's coming from UAN or it's coming from manure. Um, it's ammonium, right? So it's going to go through this nitrification process. Now, between fertilizers, is there some chance that there's different efficacy? Maybe. But the hope would be that if they're effective in one case, that they would be effective in the others. And then the final thing that I'll point out here before we jump in is that a lot of what you'll see today in this presentation is going to be related to the nitropirin and the DCD products. That's what there's research on. There's not much research on Centuro, though I do have a few slides in here that have data from trials using Centuro. And then beyond that, there's not really, like I said, much research on these kind of alternative products. And so I won't have any of that for you today. Okay, so jumping in, the first few slides here, what we'll be looking at is the effect of these nitrification inhibitors on soil nitrogen. In this case, when I'm saying soil nitrogen, what I mean is plant available nitrogen. And in most cases, we're going to be looking at the ammonium concentration in the soils because these inhibitors are supposed to maintain the ammonium concentration in our soils. So, this first study that we'll look at data from is from the University of Illinois. The study was conducted back in 1975. And what we're looking at here is a comparison of 120 pounds per acre of nitrogen as anhydrous with and without 1 pound per acre of Inserve. And so 1 pound per acre is about 2 times the labeled rate for Inserve. That's what they chose to do in this study. So on the figure, along the bottom axis, as you move from left to right, you're getting further away from the time of application of the fertilizer. And then on the y-axis, on the left side of the plot, as you move from the bottom to the top, you're increasing the ammonium concentration in the soil. So, if these inhibitors are working, what we would hope to see is greater ammonium concentrations in the soil where we have them than where we don't. And what you'll notice is the gray line on this figure is where we have Inserve, and the black line is where we do not. So you can see that kind of regardless of the number of days after application, we're maintaining higher ammonium concentrations in our soil, meaning that nitrogen has the potential to be more protected in that scenario. And the other thing that I'll kind of point out here is if you actually just look at the lines themselves, you'll notice that the gray line has a much more gradual decline over time versus the black line has a pretty sharp decline from, up between 0 days and 150 days. And then after that, there's almost no change because has dropped almost to zero. And so that's another indicator that this Inserve product is reducing the rate of nitrification in our soils, even up to 240 days after we apply the nitrogen. So, this next study that we will look at is from North Dakota State University. It was conducted in a lab, and what they were interested in understanding here is how does the concentration of the products that we apply affect how well they perform. So on the bottom, on this figure, where you see inhibitor concentration, as we move from left to right, what that means is we're putting more of the product in the soil. And so you can kind of think of this analogous to application rate of these products in the field. And again, on the left-hand side, on the y-axis, we have ammonium concentration in the soil. And so the higher up you are, the greater the concentration. So on this figure, the blue line and the red line, which you see up towards the top, those are going to be our nitropirin products. You can see that they were pretty effective. They maintained high ammonium concentration in the soil with relatively low application concentrations. The green line that you see kind of cutting a diagonal across, that's going to be our DCD product. So in this case, that was a straight DCD product, only DCD as the active ingredient. And what you'll notice is that there's a pretty linear increase in how well DCD works as you increase the concentration of the product. And this is pretty standard in terms of looking at DCD efficacy. How well DCD performs is really highly tied to the concentration of the product that you get. So if you're going to use a DCD product, make sure you're checking the label and getting the one that you can find with the highest percentage of DCD as the active ingredient. Then the other thing that I want to point out on this figure is quite often there's a thought that ammonium thiosulfate may provide some nitrification inhibitor properties. And I know personally a lot of farmers that use ATS. They're not necessarily using it for that nitrification inhibition, but they are using it and they are being told that it can provide some of those inhibitor properties. And so I think it's important to notice here, and actually on the next slide I'll show you again, that the purple line on this figure represents ATS. And what you'll notice is that that purple line is at 0 in terms of ammonium concentration, regardless of concentration of ATS applied. And so what that tells us is that it's very unlikely that you're going to get nitrification inhibition by using ATS at economically feasible application rates. And then the final thing that I want to highlight on this slide is if we go back and we look at the DCD curve on this slide, and we look at the highest application concentration, so 25 ppms of DCD, what you'll notice is that even at 25 ppms of DCD, it had lower residual ammonium concentration in the soil than Inserve or Instinct did with 1 to 3 parts per million application. I think the takeaway here is that yes, DCD and nitropyrin both provide some level of inhibition of nitrification, but it's pretty clear, and you'll see this as we move throughout the presentation, that DCD is, in general, less effective than nitropyrin products. This again is looking at how well these inhibitors protect ammonium in the soil. So here, this study was actually conducted in a lab at Iowa State University back in 1989. And what they did was they looked at how well nitropyrin, DCD, or ammonium thiosulfate inhibited nitrification in 3 different soil types, so a Harps, a Webster, and a Storden. What you can see from this table, so the first thing I'll highlight is ammonium thiosulfate was 0 across the board, right? So again, even back in 1989, they kind of highlighted that ATS wasn't really providing any of this nitrification inhibition. And then the second thing to really highlight on this table is that you'll notice that kind of regardless of soil type, nitropyrin was always about 2 to 5 times more effective at inhibiting nitrification, so keeping the ammonium as ammonium, than DCD was. So again, this is just another example of showing that nitropyrin may be a more effective option than DCD. And so this will be our final slide looking at the effects of inhibitors on soil nitrogen. This one is actually somewhat newer. This data was collected between 2010 and the fall of 2010 and harvest in 2013. And it was conducted in Boone, Iowa. And what we're actually looking at here is how well Instinct, so the nitropyrin product that is formulated for liquid fertilizers, how well Instinct inhibited nitrification when utilizing liquid swine manure. And so on the x-axis of this figure, you'll see that we have a fall and a spring. So that was soil sample timing. So in the fall, after application, they sampled on the band where they injected the manure. And then in the spring, they also sampled again on the band where they injected the manure. And they analyzed the soil for both ammonium and nitrate concentrations, which you can again see there on the y-axis, or on the x-axis. On the y-axis, what we have is the concentration of those different plant available forms of nitrogen. And then the different colors, the blue represents no inhibitor, the orange is 0.25 gallons per acre or a quart per acre, and then the green is 2 quarts per acre, half gallon per acre. Okay, so our recommended rate is going to be the orange, and then they were interested to see if doubling the rate improved the efficacy. So the main takeaway here is that in the fall, where you had an inhibitor product, you actually had lower nitrate concentrations in your soil. So that's somewhat promising that we can actually reduce the amount of nitrogen converting over to nitrate. And then if you look on the right-hand side of the figure for the spring, where you had an inhibitor, you actually saw greater amounts of ammonium. So we were protecting that nitrogen from that manure, keeping it in the ammonium form and keeping it in the soil. And then also, if you look at the nitrate, we had lower nitrate where we had the inhibitor products as well. So it's really nice to see that these products were doing what they should be doing, keeping the nitrogen as ammonium and reducing the amount that actually made it into that nitrate molecule. So that's the effect on the actual soil nitrogen. Now let's look at the effect on corn grain yield. So this table is from a book called the National Corn Handbook. It was published back in 1992. So the data probably is a bit outdated, but what they did was they went throughout these different regions and they looked at all of the published research that had been done using inhibitors. They didn't necessarily classify what the active ingredient of the inhibitors were, but they looked at time of application. In some cases, they looked at fall and spring. Others, they looked at fall, spring, and then they also separated into a spring no-till category. And then other certain regions, they only looked at spring applications. So I would encourage you to look at this table and especially if you're from the Midwest, see where you may fit on this kind of these different regions, and you can kind of interpret this table as you would. What I'll say is, for those of us from Iowa, you won't see Iowa listed on this table. According to this document, they consider Iowa to be an Eastern Corn Belt state. I think that depends on where you're at in Iowa, right? So if you're in the northern part of the state, I would recommend you look at the Northern Corn Belt region. If you're in far western Iowa, you may look more towards that Western Corn Belt. But I think the takeaway here from this table is that, at least at the time that this was published, they were seeing the probability of a yield increase from using nitrification inhibitors ranging anywhere from 10 all the way up to 80% of the time, right? And that yield increase that was associated with that was on average anywhere from, let's say, 3 all the way up to 30% in some cases. And so, while I would love to sit here and tell you that, this is going to be true and you have a, you know, uh, 50% chance of seeing a yield increase, and that could be, 10% increase. Unfortunately, as we move through the rest of the presentation today, you're going to see that it might be time that we update this National Corn Handbook, or at least put out a new publication with an updated table to give us a better idea of what the current science is saying. So, the first study that I'll share with you is actually from the University of Missouri. This was done in northern Missouri, so it was over 3 years. And they were looking at anhydrous ammonia application with and without different inhibitors. In this study, they did look at both fall and spring application timings, and they did not see a difference in yield with application timing. So that's why you only see one set of bars on this figure. So these bars are averaged across the fall and spring application timings. So along the x-axis there on the bottom, the non-treated control, that is actually where they put no nitrogen at all. And then moving from left to right, you have anhydrous plus Inserv, anhydrous plus Centuro, anhydrous plus function. So remember, that's that DCD product that has a little bit of sulfur in it. And then anhydrous with no inhibitor at all. And then you have grain yield and bushels per acre on the left. So I think the main takeaway here is that there was no difference in yield between any of the treatments except where they didn't put nitrogen at all. What this is telling us is that, at least in this case, over this 3-year study, they didn't necessarily see a benefit in terms of yield from using really any of the most common active ingredients that there are in terms of nitrification inhibitors. So, the next study I'll share with you was conducted across Illinois, Nebraska, and Missouri over 3 years. And over those 3 years, they had 17 total locations where they conducted this study. Again, in this study, they were also looking at fall versus spring application timing of anhydrous, and they saw no difference in terms of application timing. So, again, that's why you see one set of bars on the figure. On this figure, again, you have yield in bushels per acre on the left, but across the bottom, this time, our control actually represents just anhydrous with no inhibitor product at all. And then in the middle, we have nitropyrin. That's our inserve in this case. And then on the right is pronitridine or Centuro. And so I know that I know that this figure may be a little bit misleading if without context, because it might look to you like there was a pretty big increase in yield. But if you notice the scale on the left-hand side, we're pretty zoomed in terms of that scale. And so really we're talking 169 bushels with no inhibitor and maybe 175 at our highest there with Centuro. Statistically, no difference. And when you think economically, is that even enough to maybe cover the cost of the product? Maybe. You might break even. You may not. I think it depends on the year and the price of everything that you're working with. So the next study, this one is from North Dakota State University. It again was over 3 years, but in this case, their fertilizer sources were urea in the blue and UAN in the green. And so they were looking at applying these fertilizers with and without nitropyrin. So in this case, the nitropyrin product that was used was Instinct. They used Instinct, right? So that's only a nitrification inhibitor. And what I'll say is that this fertilizer was broadcast, but it was immediately incorporated after application. There was really no worry for volatilization, which can happen if you were to leave these different fertilizer sources on the surface. The main takeaway again here is that there was really statistically no difference in yields amongst any of these treatments. And when you look at maybe what was the difference in yields numerically, right? If you want to say, I don't care about statistics, just tell me what the numbers are. When you look numerically at what the differences in yields were in this case, it's possible that they were enough to maybe cover the cost of the product. But again, it depends on the cost of the actual product and the fertilizer itself. So the next look at the effect on yield is going to be going back to that previous study where we looked at the liquid swine manure from Iowa. So this is the yield data from that study. So a reminder, a 3-year study in Boone, Iowa. They injected liquid swine manure with and without Instinct at 140 pound of N per acre equivalent. And in this case, what they saw was where you had the labeled rate of Instinct, you actually had significantly higher yields than where we didn't have Instinct at all. The double rate of Instinct, there was technically no statistical difference in yields between it or the other two treatments. But what I'll highlight here is that in this case, we are looking at 188 bushels per acre for the no Instinct treatment versus 196 bushels per acre for the labeled rate of the treatment. So you're talking 8 bushels per acre. In that case, that yield increase may have been enough to cover the cost of the product plus make a few dollars. But that double rate, that absolutely would not work out economically for you. Here's the final one that we'll look at that is only yield related before we get into some kind of the environmental benefits that might be tied to these products. So in this case, this study was conducted in Indiana, and they were looking at the application of UAN at 160 pounds of nitrogen per acre, either pre-plant or side dress timing. So all nitrogen applied at one timing, either pre-plant or side dress, with and without instinct. In this table, the top row is going to be yield. So you'll notice in terms of yield, there's really no difference in yield whether or not you have an inhibitor, and really no difference in yield with application timing as well. And then I want to highlight the bottom row of this table first. So that's going to be nitrogen use efficiency, kind of in the most common way that a lot of people think about it. That's pounds of nitrogen per bushel. You'll notice no difference in pounds of nitrogen per bushel. But if you look at the center row on this table, what that represents is nitrogen recovery efficiency. The easiest way to describe what that means is if you look at that first column there, the number 40. So imagine that we had put 100 pounds of nitrogen down on this field. What that 40 means is that 40 pounds of that 100 actually made it into the corn crop. And the way that we get to that is we have treatments out there where we put no nitrogen and we look at the difference between the fertilized and unfertilized crops and see, how much of the nitrogen from in the fertilized crop came from the fertilizer. So the interesting thing to take away here is that where they had the instinct product, so where they had the inhibitor, they actually saw greater nitrogen recovery efficiency. So in this case, this didn't translate to yield. It didn't necessarily translate to nitrogen use efficiency, but we had greater nitrogen recovery efficiency, which means that theoretically we're using more of what we actually paid for. So you might ask, why is there no difference in nitrogen use efficiency in terms of pounds of nitrogen per bushel if we see greater nitrogen recovery efficiency? And the answer there is relatively simple. In the Midwest, we have pretty rich soils. We have a lot of organic matter. The corn is going to take nitrogen from where it's available. So if we have more fertilizer nitrogen available, it's going to take that up because it's easy. But if we're lacking a little bit, it's going to take nitrogen that comes from organic matter mineralization. That's how we get to the same nitrogen use efficiency, even though we have greater recovery efficiency. Okay, so let's look at how these inhibitors might affect nitrate losses. So remember, nitrate losses, we're talking leaching, so the loss of nitrogen to the waterways. So this study is from Illinois. They applied anhydrous at 140 pounds of nitrogen per acre. And what I really want to highlight on this table is the first two columns where they had a pre-plant application and then a pre-plant application with N-Serve. So what you'll notice in that top row there, that's yield, really no difference in yields. Pretty standard to what we've been seeing in terms of the effect on yield. Now, the next two rows on this table are actually related to water quality. So the center row is flow-weighted nitrate concentration. So what that means is it's essentially how many units of nitrogen are leaving per unit of water that's leaving the field. Our flow-weighted concentrations there's really no difference in flow-weighted concentrations with or without an inhibitor. And then the bottom row, this is nitrate load. So this is on average, in a given year, how many pounds of nitrogen per acre are actually leaving through the tile system. And again, what you'll notice is really no difference from having that inhibitor applied in this case. So we'll look at another study here that measured the same things. In this case, this study was done in Gilmore City, Iowa, so kind of northern Iowa. They had anhydrous at 150 pounds of nitrogen per acre, either fall or spring applied, and then with and without an inhibitor. Again, the top row, really not much difference in yield, no statistical difference in yield. The middle row, where we look at that flow-weighted nitrate concentration, really no difference in nitrate concentrations with or without an inhibitor, and really no difference whether you look at a fall application or a spring application of nitrogen. And then finally, on the bottom there, nitrate load, again, no difference with or without an inhibitor. or fall versus spring application of nitrogen. This study, I like to show this one because this one is actually a long-term study. So the previous two water quality studies that I showed were 3-4 year studies. All the yield studies that I showed were, 3-year studies. In this case, we're looking at 13 years of data. This comes from Waseca, Minnesota. They applied anhydrous at 120 pounds of nitrogen per acre. So again, here I'm going to encourage you to really just look at the first two columns because that's our true comparison, where we have the fall application and then the fall application with Inserve. So your top row, you're going to be looking at yield, no real difference. Second row, we're looking at recovery efficiency again. And again, we do see that increased nitrogen recovery efficiency using more of what we paid for. And then our bottom two rows are those water quality measures. And so you can see over 13 years, there was an average, like very small reduction. They weren't statistically different. And so even over 13 years of looking at this, we really don't see much of a difference in terms of yield or water quality with an inhibitor. We've probably all heard of carbon intensity, these new carbon markets and measuring carbon intensity on our farms and how that's related to some of the payments that we can receive. And I think the important thing to kind of note about these carbon intensity scores that we might get for our farms is that the greatest portion of your carbon intensity score is driven by N2O emissions on your farm. So practices that we can do in order to reduce N2O emissions could help us reduce our carbon intensity scores, which could help us be able to generate some revenue from these carbon markets. So I really want you to focus on the figure on the right here, where we have the red line and the blue line. And so the red line is anhydrous application without Inserve, and the blue line is anhydrous application with Inserve. And then along the y-axis, as you move up, that's greater emissions, and then on the bottom, as you move to the right, it's a higher nitrogen application rate. Emissions are about the same if you don't put any nitrogen down at all, right? We would expect that, but nobody does that. So if we start to look more on the higher end of these nitrogen applications, which is more typical of what we would see, we see that, in this case, in this study, they were able to reduce N2O emissions on their farm they're about 5 times lower. That's pretty impressive, and that will help lead to lower carbon intensity scores. The caveat here is that that's not always the case. So if we look at this study, and again, I'm going to encourage you to really focus on the figure on the right. The black is where we have no nitrogen. Red is 120 pounds of anhydrous with Centuro. Blue is 120 without. Green is 180 pounds with Centuro, and purple is 180 without. What I want to highlight here is that within a given application rate, so within either the 120 pounds with or without, or the 180 pounds, there was no difference in emissions. The way that we know that is that the letters on the ends of the bars there are the same. So in this case, we didn't reduce emissions. And in fact, numerically, we actually saw slightly higher emissions where we had the Centuro versus where we didn't. I think the thing to remember about N2O emissions is that they're very highly tied to when you apply and then also when you get rain. Heavy rainstorms can cause high emissions. If you're saturated for longer times, like we talked about up front, higher emissions, right? So it's really dependent on the individual year in terms of emissions as well, right? And finally, the last study that I'll share with you on these N2O emissions is from this study was conducted back in 2012. What I'm highlighting here is the comparisons where they used Centuro. So those first two bars on the left, that was aqueous ammonia with or without Centuro. And then the second two bars there is going to be UAN with and without Centuro. And what you'll notice is that when using the aqueous ammonia, there was no difference in N2O emissions. But when using the UAN, we actually reduced N2O emissions where we had Centuro in this study in this one given year, right? And so this kind of just highlights that the results that we can get with these inhibitors in terms of the effect on N2O emissions is really variable. One of the things is that we kind of lack long-term studies given this data to understand the year-to-year variability. And so we really need more research in this area to be certain. So the final thing that I'm going to share with you today is just some of the factors that can influence how well these inhibitors perform. So number one is soil moisture. We kind of talked about up front how soil moisture can influence nitrification. So essentially anything that can influence nitrification can also influence how well these inhibitors perform, but in different ways. I'm not going to necessarily describe this figure to you, but what I want you to take away from this, and if you want to pause and kind of dig into this figure, is that we're potentially more effective. So these inhibitors are potentially more effective in slightly drier soils. That is probably tied to the fact that some of these inhibitors are water soluble and can move with water. Other factors might be that we're influencing different microbial populations, things like that. Soil temperature. As temperature increases, nitrification increases. So that's what I'm showing here with these two figures. The one on the left, you can really clearly see that as temperature increases, the amount of time that it takes for 100% of nitrification to occur drastically decreases. And then on the right, you can kind of see the same thing. When you move from 45 degrees, which is the blue bars, up to 60 degrees, nitrification happens a lot faster. But not only is nitrification happening faster, these inhibitor products are breaking down quicker. So the faster they break down, the faster those microbes can get back to acting on that ammonium. Soil organic matter. So some inhibitor products can bind to the soil particles. So it's possible that some inhibitor products are less effective at higher organic matters, or to put it differently, more effective at lower organic matters. Soil pH. There's evidence that shows that inhibitors may be more effective at lower pHs. So kind of more in the ranges that we want to see in terms of crop production, that 5.5 to 6.5. We're going to be more effective there than if we start going above that and get above, 7, pH of 7. And then finally, soil texture. The coarser the soil, the less likely you are to see a response to nitrification inhibitors. To wrap up, we talked about the nitrogen cycle. We talked about what inhibitors are. We talked about what the science says about how well they work. And I think if I'm going to give you some take-home messages, my first would be not all inhibitors are created equal. Some do perform significantly better than others, but all do provide some level of inhibition. So my opinion is that in terms of helping to protect our nitrogen, something is better than nothing at this point in time. Yield responses to inhibitors are inconsistent, right? They can occur. They can be up to 10% or more, but there's more evidence to show that there's a lack of yield response than there is to show that there will be an increase. In terms of the environmental benefits that we might get from these inhibitors, thinking about nitrate leaching and N2O emissions, the results are really inconsistent. Even under longer term studies, we may or may not see these benefits occur. And it's very likely that, if there is a benefit, it's going to be more noticeable in years where there's ideal conditions for loss. So we're talking years with heavy rainfall. So such as the spring of 2024, at least in Iowa, there were areas that got over 20 inches of rain within a month, right? That's an ideal condition for loss, both via leaching and denitrification. So it's possible that maybe if there was an inhibitor there, maybe that's where we would have been more likely to see an effect. But I think the main takeaway is that we need more research to really understand how well these perform. We need longer term research to understand how well they perform. And my final message for you is that nitrification inhibitors are not a replacement for following best management practices. So do not think to yourself, oh, I have an inhibitor, I can go apply anhydrous when the soils are 60 degrees. No, you don't want to do that, right? As I just mentioned on the previous slide, the warmer the soils, the faster that product breaks down. So essentially, you're spending your money for that product to not be useful, okay? So they're not a replacement for best management. Okay, with that, here I'll share my contact information with you. Again, the QR code for my website. I'm happy to take emails or phone calls from anybody at any time. Thanks for joining us for another episode of Crops TV.